In this video, we'll continue our discussion of the satellite motion around the Earth or planet's motion around the Sun. And let's start with the satellite. And we're going to just consider circular orbit by a satellite. Okay, so now here's the diagram. So let's say at the center, there's this Earth, capital M. The mass is capital M. And here, there's a satellite, little m, and the distance is r. Okay, so now let's first figure out the from Newton's second law, the dynamics of the satellite. Okay, so here's the free body diagram. The only force acting on the satellite is the gravitational force Fg, and let's see, so Fg equals, the magnitude here is g mm over r squared equals mar, right, according to Newton's second law. And ar is v squared over r. Okay, so these are the two equations we can write down for circular motion. So now let's say I want to figure out, let's say, the speed of the satellite at this instant. What's the speed v here? Okay, now I can plug in the first equation, ar's expression. So we get m v squared over r. Now the 2m cancel out. And then we have 1 of r also cancel out. So we have v equals square root gm over r. Okay, so that's the satellite speed. And its period, of course, is capital T equals 2 pi r over v, right? So that will give us 2 pi r over square root gm over r. And it turns out to be 2 pi square root r cubed over gm. Okay, so that's the period as a function of the distance to the Earth. Okay, radius r. So now one thing we can see or we can discuss is that both quantities, since they are related to the distance r to the Earth center, so we can discuss if r, let's say, decreases, what will happen here, right? So if r decreases, then we can see the speed goes up, v goes up, and the period goes down. Okay, so that's the little r here, that's the period goes down. And we know Earth has radius, right? So the smallest r that we can have is the Earth radius. And then we can calculate this, the minimum period is given by 2 pi square root re cubed over gm. Okay, and if you plug in the Earth mass, the Earth radius in this equation, then you should be able to calculate T minimum. I think it's around 40 minutes. Okay, So now let's talk about the energy. Satellite energy. Okay, so let me again draw a picture. Now, since the satellite is moving, right, with velocity v, then of course it has the kinetic energy k equals 1/2 mv squared. And let's say the distance here is r, then in the previous video we talked about the potential energy definition, right? So U is negative g mm over r. Okay, so that's the potential energy of the satellite. Therefore, the total energy, mechanical energy of the satellite is k plus U equals 1/2 mv squared minus g mm over r. Okay. However, it turns out that actually k and u have more relations we haven't explored. So let's recall the this equation. Yeah, this equation here. So if I think about the 1/2 mv squared, okay, if I think about that, then it equals, let's move r to the left side and then multiply 1/2. So we get 1/2 g mm over r, okay? And that is negative u over 2, right? So u is negative g mm over r. And we have a negative sign here, make it a positive, and then multiply 1/2. So that's the relation between the k and u. K is negative u over 2. Okay? So that's why I can rewrite this total energy E in terms of, let's say, in terms of K. So I want to get rid of U here. Then I would say U is negative 2K, right? So I get negative K here. So the total mechanical energy of a satellite is negative K. Or if I want to get rid of K using U, then I replace K here by negative U over 2 plus another U, then I get U over 2. So the total energy is either negative K or U over 2. And K is always positive, right? It's 1/2 mv squared, so it's always positive. And U is always negative. Okay, from that expression. So we can say the total mechanical energy of the satellite is negative. Or in this case here, U is negative, so E is negative. So total E is negative. Okay, so these are the energetics of the satellite around the Earth. All right, so now since we talked about the energy, right? So let's talk about a concept called escape speed. And we're talking about escape speed for a satellite or a rocket. They're similar. So if I want to send a satellite out of the Earth's surface, out of the gravity, the control of the gravity of the Earth, then what should I do? So we need to use energy conservation, and we pick one initial position, and then that equals to a final position, and then we think about the speed requirement for doing that. Okay, so now let's say here is the I'm going to draw a bigger Earth, and Earth has radius RE, right? So now on the surface here, we have a little m, the satellite, and we want to give it some speed, let's say v, so that it can go up in the sky and then hopefully can escape. So now let's say at this distance, which is infinity, right, to the Earth, and at this location, we can say the satellite escapes the Earth. Okay, and the speed here is called escape speed. Let's call it VES. So now think about what kind of VES we need in order for the satellite to go all the way here to infinity. Okay, and this initial position on the Earth's surface is I, and final position is at infinity. So now let's think about energy conservation here. We have Ki plus Ui equals K final plus U final. Now what's Ki? Ki is related to the initial speed, which is the escape speed that we need. So it's 1/2 m v escape speed squared plus Ui, right? Ui is negative g mm over re, the Earth's radius, equals the final kinetic energy. So we try to find the minimum speed, which we call escape speed. So that's why we don't need to have any kinetic energy left at the final position. So you can say it's 0 here. That's the minimum K you can have. And then at infinity, remember this formula for the potential energy. When R equals infinity, this U here is 0, right? So that's why we get 0 here. So that gives us an equation to calculate the escape speed. So let's figure out what's this VES. So V escape speed equals, so there's a factor 1/2 here. We need to multiply 2 on this side. So we get 2 GM over RE. And then there's a square root. So that's called the escape speed. Now let's compare to the previous speed, this number here, this expression here, and we said that the minimum height of a satellite is this little r here equals the Earth's radius re, right? So if I plug that in, that would be the minimum satellite speed I need. The speed of the satellite along the Earth's surface, right on the Earth's surface. Okay, so now we have a factor 2, square root 2 compared to that. Okay, so that's the escape speed. All right, so now let's move on to talk about Earth energy along the sun. And we know Earth is following an elliptical orbit. So let me try to draw an ellipse. And the sun, let's say, is here in one of the foci with mass big M. Okay, now the Earth is here, little m. Now suppose I know the Earth speed right now is, let's say, v, and its distance to the sun is r. Then we can write down Earth energy is 1/2 mv squared minus g mm over r. Okay, so that's a similar formula with the satellite energy. Okay, but now I want to add one more thing here. I want to figure out its angular momentum. The angular momentum is given by r cross p, cross product p, which is R cross product MV. Okay, and we have talked about that before. So if you look at this picture, R cross MV, the direction is out of the screen using right hand rule, which is represented by this direction. Okay, and its magnitude is R MV sine theta. Okay, so sine theta refers to this angle. That's the theta angle. You can also say this alpha angle. So MV sine alpha. Okay, they're equal. So that's the magnitude. All right, so let's talk about two special places. One place is closest to the sun, and this position is called perihelion. So it's closest to the sun. And the second location is on the other end of this dashed line. That's the major axis of the ellipse. And this position is the furthest from the sun, and it's called aphelion. Furthest. Okay, so now let's label these two distances. Let's call these RP, perihelion, and this distance here, okay, let's call it RA, aphelion distance. And let's also use some parameter from the ellipse. So let's say here is another dashed line is the minor axis, and the red line is the major axis. And then we have minor axis radius B, major axis radius A, semi-major axis length A, semi-minor axis length B. Okay, and there's a parameter called eccentricity. Eccentricity, and is defined as BOA. Okay, so it's just some math definition. And for a circle, since B equals A, right? So we have eccentricity equals 1 from that definition. But in general, for an ellipse, this E is less than 1, right? So less than 1 for ellipse. Now with that definition, we can represent RP and also RA in terms of A and B. Actually just in terms of A. Okay, so let me show you how. Because RP plus RA equals 2A, right? And then the let's see, this distance I forgot to mention. Yeah, this distance from the sun to the center is epsilon times A. Okay, is eccentricity times A. So that's why we say let's see, P plus epsilon A equals A. Yeah, so RP is this length plus epsilon A equals the semi-major length A. Okay, now from there I can say RP equals 1 minus epsilon times A. Okay, and also RA do the same thing. So RA is epsilon A plus A. Then of course RA equals 1 plus epsilon times A. Okay, so these are the two relations. We don't necessarily need this one, but you can check that if I do RA plus RP, I get back to 2A. Okay, so these are the perihelion radius and also the aphelion distance to the sun in terms of the semi-major axis length A. Okay, so now with this information, we can try to write down the energy of the Earth at these two locations, and that should give us the energy conservation. So we can say EA equals EP, right? Now let's see what we get here from this equation. We get 1/2 mVA squared minus GMM over RA equals 1/2 m VB squared. VP perihelion minus GMM over RP. Yeah. This first equation we can write out. Now, second equation is about the angular momentum conservation, right? And I haven't finished when I talk about this the general magnitude of the angular momentum. So if I look at these 2 points, perihelion and aphelion, let's draw the velocity. The velocity will be perpendicular to, so VP here is perpendicular to this RP, and VA is perpendicular to RA, right? So when I do this cross product, the sine angle here is 90 degrees. So LA is its magnitude here. Sorry, LP, the magnitude here is RP MV sine 90 degrees, right? Which is just RP MVP. And similarly for point A, LA is RA, MVA. Okay, so that's the equation I need. So let me write down the LA equals LP, angular momentum conservation. We have from here RA MVA equals RP MVP. So now let's see, our purpose here is to figure out what's the Earth speed VA and VP. Okay, now for other positions, the velocity, the magnitude of the velocity of the Earth would be between these two, right? And VP is maximum because the RP here is shortest the distance, right? As distance decreases, the speed of the Earth increases. And then the lower bound here is VA. At point A, the Earth has the slowest speed. Okay, so that's why the Earth's speed is in between these two. So that's why these 2 points have some meanings. And let's figure out what is these two speed. What are these two speed at the 2 points? Okay, so now to do that, I need another page. So let's copy these 2 equations over. So first, let's simplify this first equation. Let's get rid of little m. And from the second equation, I also cancel the m, and then I also represent the, let's say, VA in terms of RP over RA times VP, okay, in terms of VP. And then I will plug in this equation. And let's see what happens. Okay, so we have 1/2 RP squared over RA squared VP squared. And let's also move this 1/2 VP squared over, okay, and that equals GM 1 over RA minus 1 over RP, okay. And since I know like RA is minimum, right, so RP is maximum, so the oh sorry, I said the opposite. RA is maximum, RP is minimum. So we know this term is negative, right? And let's change the sign here. So let's change to 1/2, okay, 1 minus RP squared over RA squared VP squared. Let's group them together and then change the sign. And right side, let's also change the sign, GM 1 over RP minus 1 over RA. Okay, now both sides are positive. Okay, so let's figure out what's VP here. And remember we said RP and RA, right? So RP is 1 minus epsilon times A. RA is 1 plus epsilon times A in terms of semi-measured axis length, right? So that's these two. So now if I use that, I will get 1 minus, so RP squared equals 1 minus epsilon squared, right? And then 1 plus epsilon squared, okay? And then VP squared equals GM 1 over RP is 1 minus epsilon times A, 1 plus epsilon times A. And let's further simplify the two sides. So I'm going to do 1 plus epsilon squared. So I get these two a common denominator, and then we have 1 plus epsilon squared minus 1 minus epsilon squared times VP squared equals GM over A. Okay, so I pull out this A, the common A, and then inside the parentheses, I want to combine them. So I have 1 minus epsilon times 1 plus epsilon. And then in the top, I have 1 plus epsilon minus 1 minus epsilon. And let's see what we get. Now first, I can do some cancellation already. So 1 plus epsilon cancel out with this power 2. And then in the numerator, I expand this first parenthesis and second parenthesis. I get 1 plus epsilon squared cancel out. And I have 2 epsilon left minus negative 2 epsilon. So get 4 epsilon here. VP squared equals GM over A. And then here we have a cancellation of 1. So I have 2 epsilon over 1 minus epsilon. So now let's see more cancellations. 2 and this 4 factor cancel out, right? We have 2 left. And 2 epsilon cancel with this 2 epsilon. So in the end, let's write down final VP here. So VP equals, I'm gonna move this 1 plus epsilon to the right side. And then let's see, so VP equals GM over A 1 plus epsilon 1 minus epsilon and square root, right? Now VP is, remember, 1 minus epsilon times A. That's exactly this term. So that's why we have VP equals square root GM over RP. And then 1 plus epsilon. And this velocity, of course, is greater than GM over RP. Okay, so if you think about these epsilons here, which is always positive, right? So that's why we have this VP greater than that. Now affiliate VA can be figured out similarly, and it turns out to be GM over RA, okay, 1 minus epsilon, okay, and since epsilon here is positive, so this one VA is always less than GM over RA, okay, so you can do some estimate of this speed in the square root, these two sides, and according to some data, and then you will see the Earth's speed at these 2 points. They're either greater than that or less than this. Okay. So the Earth's speed is in between VP and VA is less than these 2 bounds. Okay, so I hope that all makes sense. And that's about the Earth dynamics, a speed we can calculate from the energy conservation and angular momentum conservation. Okay, so that's all for this video. Thanks for watching. Okay, now if I plug in the parameters for the Earth, so for the Earth radius is about 6378 kilometers, and Earth's mass is 5.97 times 10 to the 24th kilogram. Now if I plug in all these numbers, I should be able to calculate T minimum, okay? And it turns out to be approximately 85 minutes. Okay, so that's like the minimum period one could have for a satellite. So for example, for the International Space Station, its period is about 90 minutes. Okay, and the reason for that is because it has a higher height, right, altitude, of course, than the Earth radius. So that's why its period is about 90. It's greater than 85.